So if you look at the expansion of x plus y to the n, you can see the expansions there where n is between 0 and 6. So what we're going to learn about is a method that you can use to expand any binomial raised to any power without actually physically multiplying it all out. So that's what we're going to work towards. So you should notice some patterns that are present if you look at the expansion above. So first, the number of terms is always one more than n. In the first row, x plus y to the 0, n, the power is 0, and there's one term. The second row, the power is 1, and there are two terms. The next row, the power is 2, and there are three terms. If you skip all the way down to the bottom, where n is 6, if you count up, you will see there are 7 terms. So the first observation we make is that there are always n plus 1 terms. The next observation deals with the sum of the exponents of x and y in each term. If you look at the last row, the exponent, there's only one for the first term, that's 6. For the second term, the exponents are 5 and 1. They add to get 6. The next term, the exponents are 4 and 2. They add to get 6. In every case, the sum of the exponents equals n. If we go up a couple rows to where n is 4, the same thing happens. 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4, and so on. So that's true for every row and every sum of the exponents for each term in that row. The sum of the exponents of x and y in each term is equal to n. The next observation deals with what's happening to the exponents of x. Now, x is the first term of the binomial. You're expanding x plus y to the power n. X is the first term in the binomial. And if we look at this last row again, the power on x is 6, which is what n is. The next term, though, the power on x is only 5, and then 4, and then 3, and then 2, and then 1. And the last term, we could write it as y to the 6, x to the 0. So what happens to the powers on x is that they decrease term by term, starting with n all the way down to 0. Whereas the exponents on y do the opposite, they increase from 0 up to n. You see, this first term would be y to the 0, x to the 6. The next term is y to the 1, then y squared, y cubed, y fourth, y fifth, y sixth. The last thing we'll talk about is the coefficients. So the coefficients are 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. We say that they form a symmetrical arrangement. They form a symmetrical arrangement. And those coefficients can be put in a triangular array known as Pascal's triangle, named after this Blaise Pascal, who developed this in the 17th century. So notice that with Pascal's triangle, each row starts with the 1, ends with the 1. So the top row is 1, the next row starts with the 1, ends with the 1. Each row has one more number of integers than the previous row. To get to the third row, it starts with the 1, ends with the 1. Where this 2 comes from, it comes from adding the two numbers directly above. The 1 and the 1 add together to get 2. The next row starts with the 1, ends with the 1. This 3 comes from adding the two numbers above. 1 plus 2 is 3, and 2 plus 1 is also 3. And that pattern continues. So we can do a few more rows here. Remember, each row starts with a 1, ends with the 1. To get each number after, you add the two numbers above together. 1 plus 5 gives you 6. 5 plus 10 gives you 15. 10 plus 10 is 20. 10 plus 5 is 15. And 5 plus 1 is 6. The next row starts with the 1 and ends with the 1. 1 plus 6 is 7. 6 and 15 is 21. 15 and 20 is 35. 20 and 15 is 35, and so on. And this goes on forever. But one of the applications of Pascal's triangle is you can use it to get the coefficients of an expansion. Okay? If we look at the last row in the expansion, the coefficients are 1, 6, 15, 20, 15, 6, and 1. That's this row right there. So how do you know which row of Pascal's triangle connects to the proper expansion? Well, there's a couple ways you can figure that out. Number one, with this expansion, n was 6, and that is the second number in the row. That's one way to know what row of coefficients goes to the expansion you're trying to do, tied to the value of n. The other way is that, again, when n is 6, there's one more term than the value of n. There's 7 terms. So they're looking for the Pascal triangle row that has 7 numbers. 1, 2, 3, 4, 5, 6, 7. So that's another way of knowing which row of Pascal's triangle connects to the coefficients of an expansion. So using all this, you can expand any binomial raised to any power. So again, one way to get these numbers is using Pascal's triangle, but you can also get those numbers by using combinations. 0C0 is 1. The next row would be 1C0 and 1C1. That gives you your 1 and your 1, and so on. You can also use combinations to get the numbers of Pascal's triangle. And if you were going to do an entire expansion, probably would use Pascal's triangle, but we'll see examples where we can also use coefficients. Okay, you just have to start with the first number. N equals n on the expansion. It equals the power that the binomial is raised to. So we'll see examples where we would use combinations as well. So sometimes you're going to be asked to do an entire expansion. In other cases, you're going to be asked just to find a specific term of an expansion. And there's a simple way to do that without expanding the whole thing, and that's using this general term expansion of x plus y to the power n. So this general term is on the formula sheet. T sub k plus 1 equals nck x to the n minus k y to the k. So what we're going to see is that the value of k is always 1 less than the term number. If you wanted to find, let's say, the fourth term in an expansion, you would have to let k equal 3. T sub 4 would be found by letting k equal 3 in that expansion, because it's t sub k plus 1. If you want k plus 1 to equal 4, the fourth term, k has to equal 3. N, again, refers to the power on the binomial, and k is always 1 less than the term number. X refers to the first term of the binomial that you're expanding. Y refers to the second term of the binomial that you're expanding. They're not always going to be x and y. We're going to see examples where the first term might be 2a and the second term might be negative 5. But in this formula, x refers to the first term of the binomial that's being expanded. Y refers to the second term. So again, one thing to remember is that k is always 1 less than the term number. So let's use that for this first example. We want to find the third term in the expansion, x plus y to the power 7. So we're not actually going to do the entire expansion. We're just going to use the general term formula to find the third term, t sub 3. So using that general term formula, t sub k plus 1, k would have to equal 2, because 2 plus 1 will give you your 3. Again, k is always 1 less than the term number. We want to find the third term, k is 2. So that will be n, which is 7, right? That's the exponent on the binomial. NC2, x, which is x in this case. Remember, in the general term formula, x refers to the first term of the binomial, which is x in this case, to the power n minus k, times y, the second term of the binomial, which happens to be y to the power k. So we can use our calculator to figure out what 7c2 is. That will be 21 x to the fifth y squared. There's the third term of that expansion. If we look back up at Pascal's triangle, right, because n is 7 in this case, we'd want to look for the row where the second number is 7, or there are 8 terms. We don't have it up here, but we can build it quite easily. And the third term will have a coefficient of 21, which ours does. Also, the sum of the exponents has to equal n, and it does. 5 plus 2 does equal 7. All right, so there's the answer for that one. Number 2 asks us to find the middle term of the expansion. So to determine which term is the middle term without actually expanding it all out, we'll do this. It's 2x minus 3 to the 8th. That means you will have 9 terms. The number of terms is always 1 more than n. So if there's 9 terms, the middle term would be the 5th term, because there'd be 4 on each side. So we want to find the 5th term, which means that k has to equal 4, because the general term formula says t sub k plus 1. The value of k is always 1 less than the term number. And that'll be found by going 8c4, right? nck, n is 8 because that's the power on the binomial. The first term of the binomial now is 2x. That's raised to the n minus k. The second term of the binomial is negative 3. That's raised to the power k. So 8c4 is 70. You're going to have 2x all to the fourth times negative 3 to the fourth, which is positive 81. When you raise the 2 and the x to the power 4, you're going to get 16x to the fourth times 81. So in this case, our coefficient, our final coefficient will not be 70, right? Had we looked back at Pascal's triangle and done the next row, it would have been 1, 8, 28. That is 56, 70, 56, 28, 8, and 1. So the fifth term has a 70 there, which, there it is right there. However, because we also need to multiply that by 16 and 81, our final coefficient will not be 70. It will change in this case. It is 70 times 16 times 81. 90,720. X to the fourth. Now in this case, because there's only one variable, we also can't add the exponents together to get n. But if we go back in our work, if you add these two exponents together, 8 minus 4 is 4. That's the exponent on 2x. 4 is also the exponent on negative 3. 4 plus 4 equals 8, which is n. Okay, so these types of questions are common on the diploma exam. Not necessarily doing an entire expansion, but finding a specific term in an expansion. And you can definitely expand the whole thing out, but it's quicker just to use the general term formula. For number 3, before we find the fourth term, I would rewrite this so that instead of 1 over x, it's x to the negative 1 plus x squared to the power 9. And if we want to find the fourth term, remember k is always 1 less than the term number. K will be 3. Because the general term formula says t sub k plus 1. Oops. I don't know why I wrote a 9 there. That should have been 6. And that should have been 2. Which it was, I think. It just doesn't look clearly. Okay, so again, if we're looking for the fourth term, k must be 3. So it's going to be 6c3. The first term in the binomial, x to the negative 1, is raised to the power n minus k, 6 minus 3. The second term in the binomial, x squared, is raised to the power 3, the power of k. So 6c3 is 20. And if we look back up at our Pascal's triangle, the exponent here is 6. So that, if we look for the row that has a second number of 6, that's this row right here. And we're looking for the fourth term. And the fourth term, the fourth number in this row is 20. That is our coefficient, which we got by doing 6c3. But to finish this off, you're going to have x to the negative 3 because 6 minus 3 is 3 times negative 1. And then x to the 6, 3 times 3 is 6. And finally, we can multiply the two x's together by adding the exponents and keeping the base the same. We'll get 20x cubed. There's the value of the fourth term. Now for number 4, we actually want to expand this. Okay? 3x minus 4 all to the power 3. So I'm going to use combinations for my coefficients originally. The value of n is 3. So the first term, the coefficient, initially will be found by going 3c0. And then our r value, remember it's NCR, our r value will increase by 1. N stays the same. So the next one will be 3c1, 3c2, and 3c3. Because n is 3, there will be 4 terms. And so there's our first 4 initial coefficients. So that's the first step. Second step, the first term of the binomial is 3x. For our first term, that power will be n, in this case 3. And then those powers will decrease by 1 as you go term to term. The second term of the binomial is negative 4. That will start with the power 0, and it'll increase by 1 as we go term to term. And so now we'll finish it off. 3c0 is 1. 3x all cubed will be 27x cubed times negative 4 to the power 0, which is 1. Anything to the power 0 is 1. Plus 3c1 is 3 times 3x all squared is 9x squared times negative 4 to the 1 plus 3c2, I think that's 6. No, it's 3 as well, sorry. So that's 3 times 3x to the 1 times negative 4 all squared, which is positive 16, and 3c3 is 1. 3x to the 0 is 1. Negative 4 all cubed is negative 64. So we're going to have 27x cubed. 3 times 9 is 27, times negative 4 is negative 108, x squared. 3 times 3 is 9, times 16 is positive 144, x. And 1 times negative 64 is minus 64. So there's the expansion. In this case, it might have been easier just to physically multiply out 3x minus 4 by itself 3 times. But as n gets larger and larger, this method becomes easier and easier, quicker and quicker. All right, number 5. One term in that expansion is 3,281,250x to the fourth. Determine the numerical value of a. Right, you're expanding x plus a to the power 10. So you know that n is 10. We need to figure out what k is. So we'll just leave it as k here in the general term formula. So the next part of this will be x to the power n minus k. Again, we know what n is. We need to determine what k is. Times a to the power k. And that must equal 3,281,250 to the fourth. So if we look back at the left side, we only have a base of x in one spot, in this middle factor. The power on x here is 10 minus k. We need to find the term where the power on x is 4. So 10 minus k has to equal 4. The only place on the left we have an exponent on x is where the exponent is 10 minus k. We're looking for the term where the exponent on x is 4. So 10 minus k must equal 4. So by inspection, k has to equal 6. And you could solve for k algebraically as well by adding k and then subtracting the 4 from both sides. You'll get the same thing. K must equal 6. So now we know that k is 6. And our term will be 10c 6 x to the 10 minus 6 times a to the 6 has to equal 3,281,250x to the fourth. On our calculator, 10c6 is 210. X to the fourth, a to the sixth equals 3,281,250x to the fourth. We can divide both sides by 210, x to the fourth. We're trying to solve for a, figure out what a is. So the x to the fourth will cancel on the right. On the left, the 210x to the fourth will cancel. And we'll have a to the sixth left on the left. On the right, we need to divide 3,281,250 by our 210, which is 15,625. Then to find out what a is, we will take the sixth root of both sides. So the sixth root of 15,625 try that again. 6, math, 5 in the list. The sixth root of the previous answer is 5. So there we go. We've determined the numerical value of a. Number 6, similar to the one we just did, one term in the expansion of 3x plus by to the fourth, where b is greater than 0, is 216 x squared y squared. Find the value of b. So again, we know what n is. We need to figure out what k is, and then we can actually find out what b is. But we know that n is 4, so using the general term, it'll be 4ck. The first term in the binomial 3x is raised to the power k. The second term in the binomial by is raised to the power k. And that must equal 216 x squared y squared. You can use either the x factor or the y factor to determine what k must be. Probably the simplest would be just to use the by to the power k. The power on y must be 2. The only place we see a factor of y is right there. The power on y must be 2, so therefore k has to equal 2. It'll also work for the x, so because the power on x has to be 2, and if you look at the 4 minus k, when k is 2, 4 minus 2 will give you a power of 2 on x. So either way, k must equal 2. So we can say 4c2, 3x all to the 4 minus 2, by all to the power 2 has to equal 216 x squared y squared. So 4c2 is 6 times 3x all squared will be 9x squared times b squared y squared equals 216 x squared y squared. And we need to solve for b. And we are told that b is greater than 0, positive. So on the left, I'm going to divide both sides by, well, your 6 times 9 would be 54 x squared y squared. I'm going to divide both sides by 54 x squared y squared. So 9 times 6 cancels with your 54. Your x squareds cancel. Your y squareds cancel. You're left with b squared on the left. On the right, your x squareds cancel. Your y squareds cancel. So you'll have b squared equals, if you divide 54 by 216, I think you're going to get 4. Sorry, 216 by 54. Yep. And normally when we take the square root of both sides and we're solving an equation, we'll get a positive and a negative answer. But we are told in this case that b must be greater than 0. So therefore b equals positive 2, not negative 2. Okay? So for practice, you can work on these questions. I will post these solutions to Google Classroom so you can check your answers. So Monday will be our last lesson on this. Tuesday will be our Chapter 11 quiz, which means Thursday will be our unit exam on Chapters 9, 10, and 11. Okay? So you should work on these for practice.